Hey Stats class, in this video we're going to talk about some problems in 10.2 homework set. What we're doing, this goes a little bit beyond what we did in 10.1. So in 10.1 we determined does a linear relationship seem to exist between two variables. In 10.2 we're quantifying that relationship, meaning we are coming up with a line, not just observing that a line describes what's happening relatively well. We actually are coming up with that line that does the description of the relationship between the x and y variables, and then using that line to make a prediction about a value in a data set. Alright, so what we're going to do here is look at these summary statistics, and I got a spreadsheet to help me with the calculation, but we're going to look at these summary statistics and determine, do we have correlation there, and does that allow me to then say there is a linear relationship. That's the first part of this. So we're taking our significance level. This basically, it's just a hypothesis test. So we're taking our significance level there of 0.05, and we're looking at our p-value of 0.001, and that lets me know if there's correlation or not. When the p-value is less than alpha, there is correlation. So the way these hypothesis tests always work is the null hypothesis says there's no correlation in the population. Now, this is the Greek letter rho is what we use for population correlation. We use R for a sample. But the null hypothesis is there is the correlation in the population is 0, meaning there is no correlation. The alternate hypothesis, H1 or HA, just depending on what you want to use for that notation, says that rho is not, it's significantly different from 0. So we're getting R right here that's used to determine the test statistic and the p-value. And based on that number, we look at the p-value and compare it to alpha. The p-value is less than alpha. And because the p-value is less than alpha, remember that means we reject the null hypothesis, which is this. And we have significant evidence that suggests the alternate is what's true. That rho, the correlation in the population, is not 0. So this suggests, again, that the correlation that we're observing, even though it's only 0.3, it's not a great linear relationship. But there's enough there to suggest that a line, using a line to predict, would be better than using the average. Like the average would be like a horizontal line, and you're using the same number for all values. But you can see, just with my drawing, that when there is a linear relationship, the numbers that are up high, at the right end of that, the x coordinates, are up higher than those on the low end when there is correlation, or positive correlation in this case. So the slanted line does better than the horizontal line, the mean, for some of the values that are on the extreme ends. So that's the idea here. That's why we use the line when the p-value is small, when the p-value is less than alpha. But when the p-value is greater than alpha and we reject it, well, that would mean that the null hypothesis was true, which said that the correlation was 0. And if the correlation was 0, then the data set would be all scattered, and the line of best fit would roughly be slanted. Not slanted anyway. It would be virtually horizontal, because R is part of the calculation of the slope of that line. And so it would be virtually horizontal, and the predictions you'd be making would be using the mean anyway. So in general, when this happens, when the null hypothesis is not rejected, then we have we use the mean of the y's to estimate everything. Okay, that would be our estimation. We're using that y according to that line is that horizontal line is the predicted value for all values. But when it's slanted, we get different values. Okay, we will get a slanted one here because that p-value is less than alpha. So we are going to use the line. All right, so I'm going to write over here to the side. I like to use labels. So I'm going to say this is the slope. This is the y-intercept. All right, those are given to me here. This is the y-intercept. So the number with the x, the 1.15, is the slope. The number without it is the y-intercept. So 1.15 is my slope, and then my y-intercept is the negative 106. All right, the male who's 185 centimeters tall. So the first thing you want to do is look at your range of data. Heights from 134 to 193 centimeters. that's in there. If that wasn't in there, the line of best fit may or may not be useful. It's what we're doing is called extrapolation in it, and it's making an assumption that this linear pattern continues on beyond our data. So it's not always the case. So when we have, again, strong correlation, the p-value is less than alpha, we're going to use this line to make this prediction. So this is an x. It says the predictor variable x is the first variable given. So that is our height. So this is a height because of the unit of centimeters, and we're predicting the weight because that's kilograms. That's y that's missing that we're predicting. All right, I'm going to put x down here. I'm going to put the 185. All right, and here's what I'm going to type. To get the y, I'm going to do y equals, and I'm just doing this equation, the negative 106, so I'm going to click that, plus 1.15, click that, times my x value. So there's what I get, 106.75. There's my prediction. Okay. Now I could also, just so you can see it, just down here in a blank cell, I could just type equals, and I could just type the numbers in. Negative 106 times 1.15. I'm sorry, negative 106 plus 1.15 times, and then x was 185. So I don't have to have them as cells. I can just do all the math, but you do have to have the equal sign in front before you do it.